In this video, which is our final video in the sinusoidal functions unit, we're going to go through how to solve sinusoidal equation, or sorry, trigonometric equations. However, they will focus in on ones that are more complicated than the ones we would have done in pre-calc 11.0, because we already have done those. So, having said that, the first thing we're going to look at is just what do I mean by a trig equation? Well, a trig equation is something of the nature where you have some trig function and you're trying to figure out when does this trig function, for example, equal a half. So if you just think graphically, visually, how does this work? It says here a couple of kind of leading questions. How many answers is there? Where are these answers? Well, sine of x is this graph right here. And if I said, well, where is the graph of sine of x equal to a half? Well, this is a half. So on our graph, if we looked at this, sine of x is a half there, and there, again over here, again over here, there, and there. Now, in terms of where these angles are, or what these answers are, there's an answer there, and there's an answer there. Now, if I check my scale here, my scale is going by 20, so it's 20, 40, 60, 80, 100 degrees. So this one appears to be halfway between 20 and 40, so it looks like at about 30. Well, that shouldn't surprise us because I think we're supposed to know from special angles the sine of 30 degrees is in fact 1 over 2. So if I put 30 degrees in there, yes, I would get a half. The other one, if I look at it, so I got 20, 40. It appears that it's halfway between these two, so it looks like it's at about 150 degrees, my other answer. So those would be the two angles between 0 and 360. 360 would be right here. So how do you know that? Because I know that a sine wave makes one full pattern between 0 and 360 if it's just sine of x. Well, then all of a sudden you get more answers here, and this isn't new. We did this last unit or last semester in pre-calc 11. To get this angle, then translate to what's this angle over here? If you know that the period is 360, if you're talking degrees, what happens is these angles repeat themselves 360 degrees. So if I was here and I added 360, so if I went this way and added 360, I should get another answer. So 360 plus 30, so 390 degrees. If you find the sine of 390, you will also get a half. Add another 360 to this one, and you would get 510, which would be another correct angle. Well, what I'm trying to get you to understand is this pattern, if there's no restrictions on it, that could go forever. So once you get these two angles, you'll remember last year we talked about last semester, we talked about general solutions. And general solutions, what we did is we found the angles between 0 and 360, and then we went plus. We also went minus 360. So if you had this angle and subtracted 360, if you went here and you minus 360, you'd end up there. If you minus 360 from this one, you'd end up at these negative angles over here. And of course, that could continue in that direction forever. So once you identify your first couple of angles, then it's just a matter of adding and subtracting 360. Well, we didn't really understand the whole notion of the period and what these graphs look like when we were doing this in grade 11. Now that we've got a better sense of that, what we should be able to then say, well, what if the period, so what if it's not just x here? What if I'm solving for, if you look at my next example, what if it's the cos of 2x equals a half? Well, if you look at our graph, what happens is I've kept the scales exactly the same. It's now making two waves from 0 to 360. So if I was to get my two answers here, so a half is here, so there's one angle there, there's an angle there. That would be your 20, so that's 30 again. And This angle would be 150 again. So I still have my 30 and my 150. This is where now we're talking cos. Now the last graph was sine. Now that's two possible answers. Now here's where it's different. Because in this graph, it's 2x. Think of when you graphed sinusoidal relations. Well, when you put a 2 here, we're supposed to know that that's going to make the period of this graph now only be 360 divided by 2. What will happen now is the pattern is going to repeat itself, not 360, it's going to repeat itself every 180. So once you get these two angles, you're going to have to look at the k value in the question, and that will determine what you're going to plus or minus to get the other answer. So in this case, because the period is only 180, what we're now going to do to get, so this angle right here, I'm not going to add 360, I'm only going to add 180. Again, reason being because the period of the graph's not 360, it's 180. This one, add 180, you'll get another answer there. So the only thing that changes is that we're going to add and subtract whatever the period is. So that's the key. We got to figure out what is the period of each graph, and then we will use that to determine multiple answers for a given trig equation. Now, these are very, very basic examples just to get you that whole sense of how, if the period changes, how that changes what we're going to add and subtract. So let's move on to what we're really going to be interested in. So this is the type of equation that we're going to be dealing with. So in this question, you may look and say, oh my goodness, this is getting pretty complicated now. And it is to some extent. However, the first thing that we're going to do in these equations, or I do it in the beginning, at some point, you need to figure out what is the period. Well, this number here is your k value. So I'm just going to go over here and say the period is always 360 divided by that number. And if you take 360 and divide by 24, you get 15. So this graph is going to repeat itself every 15 degrees. It only takes 15 degrees to make one full wave. Now, having said that, our goal here is to solve for x. Well, nothing changes in regards to solving an equation. The first thing you do is you try and isolate. You want to get x by itself. Well, to do that, there's a bunch of stuff that we're going to have to get rid of. Just switch here. So I'm going to have to get rid of that coefficient. I'm going to have to get rid of that -3. And then eventually I'm going to have to get rid of the trig function. And then we'll have to get rid of this other stuff inside. So you got to kind of rearrange the equation. We put our pen back again here on the go. Well, first thing I'm going to do is this number here, I'm going to move it to the other side. So my equation becomes -5 sine 24 on x plus 4. And now it'll equal 1.75 plus 3. So it's going to equal 4.75. So that moved that over to that side. Well, now I'm going to deal with this -5 out in front. So I'm going to divide both sides by -5, -5. And I'll have the sine of 24 multiplied by x plus 4 equals, I'm going to divide this out so I have the actual number here. So 4.75. Divide that by a -5, and I get 0.95 negative. So this one is going to be -0.95. Okay, now this is where sometimes students that don't quite understand how trig functions work, they say, oh, now I got to get rid of sine. Oh, I just divide by sine. That makes no sense. It'd be like me sitting in the front of the room and say, okay, take out your calculators. I want you to find sine. Well, hopefully you'd stare at me and say sine of what? A trig ratio, trig function by itself without an argument doesn't make any sense, doesn't mean anything. You can't just divide by a trig function. No less than you can just say, oh, I'm going to divide by a multiplication sign. That doesn't make sense. You have to undo a trig function. You say, well, how do you undo a trig function? So in order to get rid of or eliminate sine, you must do what's called the inverse process. Well, we know from our experience that the inverse of sine is the operation on your calculator, or that we refer to as inverse sine. If you take the inverse sine of the sine, that will undo that. Well, whatever you do to one side, you have to do the same to the other side. So this is going to become inverse sine of that. So as we were saying, the inverse sine of the sine is going to get you down to 24 x plus 4 equals, I'm just going to write this out here for a second, inverse sine of negative 0.95. Now at this point, it's going to draw upon your knowledge from pre-calc 11. We have to find the two possible angles that would be associated with this if you were doing it just between 0 and 360, like a regular old trig equation. So if you can recall from last semester, we looked at an angle in the first quadrant, an angle in the second quadrant, an angle in the third quadrant versus an angle in the fourth quadrant. And then we also had, some of you use this, it's kind of an acronym for where trig ratios are what sine. We also had the whole notion of if it's sine, it goes with y. So it's if I look at this and say sine is negative, that means the y is negative. So I would know from this, I'm talking about two angles that are situated down here. Now, based on our knowledge of trig functions, and now we know what the graphs look like, it makes sense that if I'm getting a negative sine ratio, well, negative sine ratios are down here. So I know my answer's got to be somewhere between 180 and 360, which is what on a unit circle graph or representation is exactly what we would have said in the same thing. So this just kind of hopefully gives it more reference just based on your now more knowledge of what these functions look like when you graph them. So what we got to do is figure out, well, what are the two angles down here where the sine ratio equals that number? So the way we do that, if you can recall, reference angle is some number, and then we put Q for quadrants. Well, we've just identified it's got to be down here in the bottom. So that's 3 and 4. Take your calculator, make sure it's in degrees, and go inverse sine. Don't put the negative in your calculator when you're finding a reference angle. So I'm just going to type in inverse sine of positive 0.95. Do that here. Second function, sine. And I get 71.8. I'm going to carry one decimal place with these. I know we say 3 often, but I think for these ones, we'll just go like that. Up, I'll just go back here for a second. Up here, you're eventually, because this is a trig function, you're eventually going to take the inverse sine or inverse cosine of both sides. You're going to want to carry at least 4 decimal places here. Now, this one was exactly that, so I didn't have to worry about it. But if there had been more digits there, I would have carried 4 places, knowing that I'm going to do inverse trig function of it. Okay, so now I'm going to figure out what are the two possible angles. Well, the two possible angles, if I go with 71.8, there's one here and one here. So I'll just call them theta 1 or whatever you want to call it. So theta 1 is 180 plus 71.8. Well, that's going to be 251.8. The other possibility that we could be talking about for this situation would be the angle in quadrant 4, which would be 360 minus 71.8. 360 subtract 71.8, and I get an angle of 288.2. So that's here. So this should look very familiar from what we did in pre-calc 11. Now, what I'm going to do is go, so these are the two possible values for this right side of the equation. So instead of inverse sine of negative 0.95, I'm saying that this value, or this is talking about an angle. This angle on the right side could be this, or it could be this, because there's two possibilities. So what we're going to do, and then I kind of jumped over this, but We're then restricted here in the beginning that we're only going to accept answers for x that are somewhere between -10 and 80. Now we'll see how that plays out here in a moment. So what you need to do is make two equations. The left side is unchanged. 24 onto x plus 4 could equal, so instead of that mess, we're going to give this as one possibility. Or this left side, 24 onto x plus 4 could be equal to 288.2. And now, these are just now linear equations. You just solve for x. So rearrange and solve for x and see what you get for answers. X plus 4 would equal 51.8 divided by 24. That gives me 10.5 roughly. Then I'm going to subtract 4 from both sides, which should get me 6.5. There's one answer. Go over here and do it again. X plus 4 could equal that number divided by 24. So 288.2. 288.2. Divide that by 24, sorry. I get 12.008. It just depends on how accurate you needed these. We carry one there, whatever. So x equals, now subtract 4 from that, I should get 8.008, let's say. Now, go back to your boundaries that you were given in the question. -10 up to 80. So I'm going to look at my two answers that I got. Sometimes you might get answers here that are not even between those two bounds. They're not even actual answers, but they're going to help you figure out the answers. So in this case, though, these two numbers are both somewhere between. I'll just put it here so we can see it. Our bounds are -10 is less than or equal to x, which is less than or equal to 80. So I'm only going to accept answers between those two numbers. These two are, so they're good. Now, how do we get more answers? Because remember, sinusoidal relationships just repeat themselves in this wave pattern over and over. That's where knowing the period becomes critical now. Because of this k value being something other than a 1, the period of these graphs is 15. So what I'm going to do is take each of these answers that I got, and I'm going to add and subtract 15 until I no longer get answers that are within these bounds. So let's take 6.5 first. Let's try taking away 15 and see what that does. So if I have 6.5 and I subtract 15, I will get -8.5. That would be okay. So there's another answer. X could be -8.5. Again, what all I'm doing here is plus or minusing the period, which in this case is 15. If I was to take away another 15, I think you'd all agree we're going to get something smaller than -10, so I can't subtract 15 anymore. However, I could add 15 to this. So 6.5 plus 15 would be 21.5. That would be another possible answer. So I'm going to keep adding 15 until I no longer get, or until I go beyond 80 degrees. So I'm going to try another 15. So add 15 more. I'm at 36.5. Still good. Add another 15. 51.5. Add another 15. Still good. 66.5. I try another 15. Now that gave me 81.5, which is, I can't write that as an answer because it's not between -10 and 80 as our domain was outlined. All right, so I got 1, 2, 3, 4, 5. I did 6 possible answers there. Go over here. Let's take 8.008 and let's subtract 10. So 8.008, and I take away the period. Sorry, so 15, not 10. Take away 15 is -6.99. There's a possible answer besides that one. -6.992. If I was to take away another 15, That's going to give me negative 20 something, which is smaller than this, so it's no good. You can't take away any more. So I'm still here now just adding and subtracting the period. So now let's try adding 15 as many times as possible. So I add 15 to this and I get 23.008. Add another 15, 38.008. Keep going. And you say, how do you know you keep going? Because I still haven't got an angle that's bigger than this one. So I know there's more. So add 15 more. I'd be at 53.088. Add another 15. I'd be at 68.008. Add another 15. That would take me to too much, right? Because it's going to give me 83 point something, and that would be more than 80. So I get 1, 2, 3, 4, 5, 6. So I got those 6 answers. So any of those 12 answers, if you were to take them, put them in the original question for x, okay, so wherever you see x, if you fill in any of the 12 answers we got here and type this left side into your equation, you will get 1.75. Now, it might not be exact just because of rounding, but it'll be very, very close to that particular answer. I always tell students that at this point, these questions, it's great that they fall at the end of this unit because they are about as all-encompassing as you can think of a question to be in order to make sure students really, really know their stuff about trigonometry. You have to know your stuff to get these right. So kind of a good summary exercise to force you to go through these. Okay, so let's get going now with a few of these. So this one, I see here pi over 6, so we're in radians this time. There's in radians. Express your answer to the nearest hundredth, so it wants 2 decimal places. All right, away we go. So let's isolate first. So I want to start moving things around. I'll bring the 14 over here and I'll get 2 equals 6 cosine pi over 6x. Divide both sides by 6. That gets me down to 1/3, right? 2 over 6 equals the cosine of pi over 6x. I want to get rid of cosine. So that means I have to take the inverse cosine of both sides. Inverse cosine, inverse cosine. So I'm down to the inverse cosine of a third equals pi over 6x. All right, rely upon your knowledge of trig to figure out what are the 2 possible angles this could be referring to. I'm just going to put some scratch work over here. So cosine, then cosine goes with x. Cosine of an angle is the x over the r. This time it's positive. Well, cosine can only be positive here and here then. So we know we're talking about an angle in quadrant 1 and an angle in quadrant 4. If you're now understanding the whole wave idea better, one answer is here, cosine's positive. The other one's over here. That makes sense. This is the one between 0 and 90. This is the one between 270 and 360, which would be quadrant 4. So the graph makes sense with what we were doing before. Now, use your calculator and go inverse cosine of a third, and that'll give you the reference angle. Make sure it's always positive, and then we're going to put it in the quadrants we identified above here, 1 and 4. All right, so let's figure out what angle we're talking about. 1/3 inverse cos 70.5. So I'm going to go a couple, so let's go 70.529 just to keep things more accurate. 70.529 in quadrant 1, so that's one possible answer. So theta could be 70.529, or it could be 360, the one down here. 360, take away that reference angle. So 360, it would be 289.471. So these are the two possible outcomes or values of angles associated with this expression over here. So we're going to write out two equations. 70.529, that could be one value for this, could equal the right side. Or this angle could be the possibility for that one. 289.471 could equal pi over 6 times x. Oh, no, I messed up. This is why I miss having you guys around to help me. I forgot one major thing here. We're talking about angles in radians, not degrees. So all I gotta fix, I gotta go back here. I did these as if they were degrees. I need to switch my calculator to radians and get my answers. So let me fix that here. And instead of this should have, that was fine. This one's got to be 2 pi, not 360. So it's going to be 2 pi, because we're in radians, not degrees. 2 pi minus theta. So my reference angle, I'm going to have to fix that. That's not going to be right. So we're going to fix this, which will then change these two answers. Thank goodness I found that before I continued on. Which will then change these answers. I'll come back and just fill them in here in a second. Okay, so now let's get our calculator in radians instead of degrees. So okay, good. I'm in radians now. I'm going to go same thing. So 1/3 inverse cosine function cosine, and I get 1.231. That's my reference angle. 1.231. So in quadrant 1, the answer would be 1.231 radians. In quadrant 4, again, you're not going to use 360. You're going to go 2 pi minus this angle, which is the radian version of it. So 2 pi. Use my calculator. I'm not familiar with here. 2 pi subtract 1.231. And I'm getting 5.052. 5.052. Okay, so let's go over here and put these answers in instead of the degree version. So 1.231 could be one possible angle in radians equal to that, or 5.052 would be another possibility in radians equal to that. So now we're going to solve for x. So we're going to multiply by 6. Actually, just do it all at once here. Just multiply this side by 6 over pi. That'll cross the 6 and the pi out. You got to do the same to this side. And that will give us an answer for x. So let's see what I get. So 1.231. 1.231. Multiply it by 6. And then divide your answer by pi. And I get 2.351. Over here, do the same thing. Let's multiply by 6 over pi. I'll cross the 6 out and the pi out. Multiply here by 6 over pi. And I'm going to get 5.052. Multiply that by 6. And then divide that by pi. And I get 9.649. 9.6. Try that again. 9.649 would be another possibility for x. Well, the difference this time is we were not, oh, I ignored something else too. They said nearest hundredth. Let's see what they asked. 2.35, and x would equal 9.65. Following their instructions, nearest hundredth. Okay, now I got to figure out, it just said general solution. What you're going to figure out now is, well, what am I going to add and subtract to each of these to get more possible answers? Well, we're going to have to look at the k value. In this question, the k value is right here. It's always a number in front of the x. That's k. We're going to use that to figure out the period. We're in radians, don't forget that. So over here, let's just do a period calculation. Again, knowing that k is pi over 6. So the 2 pi over k, k being pi over 6, always equals the period. Well, when you divide by a fraction, you multiply by the reciprocal. This is really going to be 2 pi multiplied by 6 over pi, which is going to cross those out. This graph has a period of 12, and that's in radians. So all I'm going to do here, here's my what are called the general solutions. So your general solutions, meaning there's no restrictions on the bound, it can go forever. General solutions would look like this. And there's a variety of ways you can write it out. I'm going to go with one possible answer could be 2.35 plus or minus 12k. That means multiples of 12. Add and subtract them. Where k could be any element of the natural numbers. The other possibility would be the same thing, 9.65 plus or minus 12k, where k could be any element of the natural numbers. You can recall, hopefully, from last unit where you can also just put a plus sign here and just change this to integers, and then that will account for putting negatives in there. It would be the same thing. There are your general solutions of that trig equation. Okay, so you do got to be really careful with these, that when you get going, you don't overlook the whole radians degrees, because it's really important which mode your calculator is in, depending on whether the equation is built to model degrees or radians. All right, so let's have a look at this one. So we can tell in this one that we're in degrees, because I see the degree symbol here. I see my restrictions are in degrees, so I'm good to go. I know I'm in degrees. All right, so I got to solve for x, which is in here. So let's start whittling away things. I've got 6.2 sine 4x plus 8. I'm going to move that minus 1 to the other side. That'll give me 5. I'm going to divide both sides by 6.2. And that's going to leave me with sine of 4 onto x plus 8 equals, divide this out, so 5, divide that by 6.2, and I get 0.8065. This is what I mean by carrying 4 decimal places, because I know to get rid of that trig function, I'm going to take the inverse trig of this. So for trig functions, to get your angles as accurate as possible, you want to carry at least 4 decimal places. 8065. Oh, I screwed that up again. Oh, no, sorry, I haven't used trig yet. Now I got to make sure I switch back from degrees to radians. And this, you see what I mean by if I hadn't thought of that before I get to here. So now, if I hadn't thought of it, I would have been in a mess again. Take the inverse sine of the left side, take the inverse sine of the right side, and you will end up with 4 onto x plus 8 equals the inverse sine of 0.8065. So then I usually just kind of go off to the side here. I have to figure out what are the 2 possible angles that I'm talking about here. Sine can be positive only here or here. So we know we're using theta and we're in degrees. So it's 180 minus theta. Take your calculator, make sure you're in degrees, and go inverse sine of 0.8065. Get your reference angle. I'm getting 53 point. This one didn't give me any restrictions. Let's carry 1 decimal. Let's go 53.8. That's my reference angle. And it could be in quadrants 1 or 2. So my possible answers for this is always talking about an angle on this side. So the possible answers for that angle are 53.8 if it was in quadrant 1, or if it was in quadrant 2, it'd be that minus an 80 minus that angle, I would get 126.2. So these are the two possible values for the right side. That's going to generate two equations here. 4 on the x plus 8 in here. Oops. Okay, so 4 on the x plus 8 could be 53.8, or it's not that. It could be 4 on the x plus 8 could equal this angle. That's the other possibility. Solve for x. Divide both sides by 4. X plus 8 equals, I'm just going to leave it like that for a second, so I just put all my calculator at once. And then I'm going to get rid of the add 8, so I'm going to take away 8 from both sides. And x would be 53.8 divided by 4, take away 8. That's going to give me one possible answer. Let's do that out. So 53.8, divide that by 4, and then subtract 8. 5.45. So one possible answer is 5.45. Over here, divide both sides by 4. X plus 8 is 126.2 divided by 4. And I'm going to have to take away 8 from both sides. Take away 8, get rid of that. So x is going to be, whatever this comes out to, 126.2. Divide that by 4, and then subtract 8. And I get 23.55. All right, now to get more possible answers, because of the fact that these sinusoidal, both sine and cosine, are periodic, I'm going to need to figure out the period. So I need to identify the k value. Well, the k value was right here, the number in front of this after you've got a 1 here, so it's a 4. Remember, to get the period, it's always 360 divided by k equals the period. So 360 divided by 4, in this case, gives us a period of 90 degrees. Now, this one had bounds, or a restricted domain. It's only going to allow me to use answers between 0 and 360. So I can't take away 90 from these, because that's going to give me negatives. So you know that those are the two smallest possible ones. Let's get some more. What did I say? I think the top number is 360. So if I take each of these now and keep adding 90 till I don't go over 360, so I'm going to add 90 repeatedly to this one, and then I'm going to add 90 repeatedly to this one, knowing the biggest number that I can get for, I guess it's x, not theta, is 360. So 5.45 plus 90, that's 95.45. Add another 90 to that, that's 185.45. Add another 90 to that, and we are at 275.45. If you were to add 90 to that, you'd be at 365.45, which would be more than your upper bound here that you're allowed. So that's it. It's those 4 off of that one. Now let's take this one. 90 added to 23.5 would give me 113.55. Add 90 to that would give me 203.55. Add 90 to that, 293.55. If you tried to add another 90, you'd be beyond 360. So you get 1, 2, 3, 4, 5, 6, 7, 8 possible answers to that trig equation. I think the 3 examples now you can rely upon. I'd rather show you rather than another one of those. Now, the key to that one is I'd have to switch my calculator back to radians, and then I go through the exact same thing that I just did. Let's look at this application one. I usually would ask students this type of a question on an exam or a test. I'll give the function. So here's a function, and it tells you here that this function, it says that one of the main food sources for the Arctic fox is the lemming. Suppose the population L of lemmings in the region is modeled by this function. So this function is telling you the population of lemmings. I think I must have cut off the other part. T stands for what year it is in the study. So T is years. So part A simply says, what is the lemming population in year 15? Well, that wants me to just put 15 in for T. So part A is just L at 15, meaning put 15 in where the T is simply 5,000 sine pi over 12, 15 minus 12. It doesn't group these, but if you're going to type this in your calculator, that's all the argument. That's the angle, so you'd have to make sure that's grouped in a bracket when you put it in your calculator. And then it simply becomes putting numbers in your calculator like we did on our recent assignment, not assignment, but our recent practice questions on the application problems. So I've got to figure out what this is. So it's going to be one thing we should check is what do you think we're in, radians or degrees? I'd say based on this, we're in radians. Make sure your calculator is in radians. Radians, and let's figure out what this will give us. So 3. Just typing it all in here. Find the sine of that. Times that by 10,000. I'm getting rough. So we're talking about the population of an animal now, so we can go to whole numbers. So I would say we're at 13,536 roughly, if I type this in properly. The calculator I'm using is pretty old school. It doesn't let me type it all in at once, so I hope I didn't screw that up. Okay, part B, which is now what we were kind of going over here in today's video. It says determine, this is really important, the first 3 instances that the lemming population reached 8,000. So they've given me the lemming population, which is the left side of this equation. That's what it stands for, L. Now this just L of T. Sometimes students think that means L multiplied by T, but hopefully you get enough knowledge of function notation. This just means the lemming population at any time T is equal to this. So if they're saying when is the lemming population 8,000, you've been given the left side of the equation. So the good news is this one's in radians, which will give us a chance to practice radians again. I'll show you that. All right, so I got to solve this equation for T, and it wants the first 3 instances. Now we're talking about years, times. So let's start moving things around here. So I'm going to move the 10,000 over. That'll give me negative 2,000 equals, everybody okay if I just hope here if I'm going to. I'm going to divide by the 5,000 at the same time, just avoid having to write everything out as much. And that will, so if I take away 10,000, that'll give me negative 2,000. Then I'll have to divide both sides by 5,000, and that'll get me down to just this part. All right, and then we run into the situation where we have to now get rid of the trig function on the right side. So to do that, I'd have to take the inverse sine of both sides. Inverse sine, inverse sine. And this will be inverse sine of, I'm just trying to chop the zeros off, 2/5 equals pi over 12 multiplied by t minus 12. So I'm going to take this and just figure out what angles are we talking about here. So inverse sine of 2/5. I lost my negative. There's a negative here. So negative 2/5, sorry. Okay, sine can only be negative where y is negative, down the bottom too. So down here, we're in radians now. So it's pi plus theta, or 2 pi minus theta. So let's figure out the reference angle. and then put it in quadrants 3 and 4 on the bottom. Remember, when you find the reference angle, do not put it in your calculator. So I'm going to go 2/5. Make sure you're in radians, inverse sine, and I get 0.411. So the two possible angles, first one will be down here, pi plus that answer, or that reference angle. So if I just add pi to that, I get 3.553. There's one possible value for the left side. The other possible value for the left side is 2 pi minus the reference angle. So we're going to go 2 pi, and then I'm going to subtract 0.411, and I get 5.872. All right, let's go rewrite our equations and see what we get here for answers. Okay, so this could be 3.553. 3.553 could equal pi over 12 onto t minus 12, or it could be 5.872, or 5.872 could be equal to the right side. And we have to solve each of these. All right, here we go on our calculator. So to get t by itself, I'm going to just kind of start doing a few things at once. I'm going to have to multiply both sides by 12. So 12 times 3.553. That would equal pi onto t minus 12. Then I'm going to have to divide by pi. Divide that side by pi. That would get rid of that. And then I'm going to have to add 12 to both sides. So at the very end, I'm going to have to type in 12 times 3.553. Divide it by pi, get that answer, and then add 12 to that, and you'll be left with t by itself. Let's see what I get. 3.553. Multiply that by 12. Divide that by pi. And then add 12. I get 25.571 as one possible answer. Then I go over here and do the same thing. 5.872. I'd have to multiply by 12. I'm just going to kind of speed this up a little bit. Divide by pi, and then add 12 at the end. And that should give me another answer for t. 12 multiplied by 872, and divide by pi, and then add 12. And I get 34.429. So these are two times when the lemming population was at 8,000, but they most likely are not the first three. There are two. If it just said, give me any two, or any three, or any five, well, these would be a good start. The next thing we had to do earlier, we need to figure out the period of this function. If you look at your trig function in the beginning, the k value was pi over 12. So let's use that. So the period, remember, in radians is always 2 pi divided by k. So in this question, it'd be 2 pi divided by pi over 12, which is then multiplied by the reciprocal if you want to figure out what it is. And the nice thing is the pi's cancel, and it works out to a nice whole number, 24. That's the period. Well, I think you can see that if I had each of these times, I could subtract 24 and get earlier times than these ones, which would coincide with also having a population of 8,000. So I'm going to take each of these and subtract 24, which will give me 20, sorry, not 20, just give me a 1. So t would equal, I took 24 off of that. So t could equal P could equal 1.571. That could be one possibility. I could not take another 24 off of that because I get a negative. We're talking about years in a study, so I can't have a negative answer in this situation. So there is our first time. There's nothing any earlier than that. You say, well, what about this one? Well, if I took 24 off of this one, so I take away 24 off of that one, again, because the period's 24, I would get an earlier time, which would be 10.429. But this is the earliest one. And again, I couldn't say, well, once you take 24 off of that, I can, but I get a negative. And based on the context of this problem, I can't have a negative year in my study. Well, that means if I was to answer their question, the first three, well, there's the first two. So here's your answer. Here, 1.571. This number would be the second one. And then the third one would be this one here, 25.571. If it said state 6 years, well, then you could use this one, this one, this one, and this one. And then you could add 24 to each of these to get two more if you needed them. But this one wanted the first three. Those are your first 3 years or times where your lemming population would have hit 8,000. All right, that is our last video on sinusoidal relations. I will put a short assignment out, follow on these final two concepts, and then we will have a summative unit assignment on everything you've done that you'll have to get turned in. That'll probably be part of next week's work. That will be followed up then by our next unit, which will begin studying exponential functions.